Hi everybody, welcome back. We're continuing on chapter 3, 3.1. We're looking at example 3 today. We're going to be determining the least common multiple. So a multiple is when you multiply the number by 1, 2, and 3. So 18 times 1 is 18, 18 times 2 is 36, and so on. So when you list the least common multiple, here's what I'd like you to do. So what you're going to do is you write the number. The first number they give you is 18. All right. And what you want to do is just start listing the multiples: 18, 36, 54, 72. And you'll notice these numbers end in zeros, so you're going to at least have to get to some numbers that end in zero in order for this to work for multiples, right? So that's what I look at when I'm doing these questions. Okay. 72 and then 90. Obviously, 90 is going to work for 30, but it's not going to work for 20 because it's not multiple of 20 would be 20, 40, 60, right? So it would be every 20, so that's not going to work. So you're going to have to probably go to at least 120 here. So let's keep going. Good mental math strategy here. So add an 18, you got 108. Add 18 to that, you get 126. Add 18 to that, you get 144. Add 18 to that, you get 162. Add 18 to that, you get 180. That should be enough. I'm not sure, but we'll give it a shot and see what happens. All right. And then the next number, what you want to do is you want to do the same thing, but this time we're going to use the number 20, right? So we're using the number 20. So the first multiple is obviously 20, 40, 60, 80, 100, 120, 20, 150. Oh, sorry, 140, my bad, 140, 160, 180. So we have another one that's the same, or our first one that's the same for both. So we're assuming that's going to be the least common multiple. I'm going to do them now. Hopefully I'm right. And the next one we're going to do is I'm going to steal some of these just to be lazy. So the next one we're going to do is 30, right? So we got 30, and the first multiple of 30 is obviously 30, and then 60, and then 90. And then 120. So you'll notice some are overlapping already. Then we got 150. Then we got 180, and then boom, 180 is our least common multiple, right? And these go on forever, right? So you can actually say da 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 da, da da da. Right? So the numbers do go on forever, but once you hit the same for all of them, you'll have them. Now remember, you could go a little further with some of these and then realize you went too far, and that's fine. I looked at it with the 20 and the 30 both ending in 0, so I knew that our 18 one had to end in 0. So it was either going to be 90 or 180. The 90 worked for 30 and 18, but it didn't work for 20, so it has to be common in all three, right? So we're going to answer the sentence, we say the least common multiple of 18, 20, and 30 is 180. All right. In short, LCM equals 180. I'm okay with LCM equals 180. So that was the first method. That's a method I like and I'm used to. But another method we can use here is we can use prime factorization. So I'm going to list the prime factors of each number right now. So an alternate method we could use is, like I mentioned, was the prime factorization. So we can write 18 as 2 times 3 times 3, which is the same as 2 times 3 squared. Do this with all numbers. The next one is 20. So I'm just going to steal this for a second. We got 20. We know 20 is equal to 2 times 5. Okay. Which is equal to 2 squared multiplied by 2 squared multiplied by 5. Then we can do 30 as well. We know that 30 is equal to 2 times 3 times 5, which that can't be simplified any further, right? There's no extras there, I guess. So what you do now is you highlight the greatest power of each prime factor in any list. So here, this would be your greatest prime factor, so we'll highlight that in the black. 2 squared is your greatest here, and 5 is your greatest here, because there's no exponent, so you pick the largest number. So the LCM, so the LCM is equal to those 3 factors multiplied together. So it's going to be 3 cubed. Well, you can list them in order, I guess. It doesn't make a difference, really. I'm just listing the 3 as I see them. Right? So the 3 that we have there above, I highlight it in black. So 3 squared, 2 squared, and 5. And then when you multiply those out, that gives you 9 times 4 times 5, which is equal to 180. So just another neat method to working on that. So you can list them just using mental math, multiplying, or you can use this second method, prime factorization method, right? Which works fine. And the prime factorization method, remember you have to highlight the greatest power in each list. So 3 squared, the highest power was squared. This had a power of 1, right? So we picked the 3 squared. This had a power of 2. 5 has a power of 1, so we picked the 2 squared. And then in the cases there's all the powers are the same, then we just pick the highest number, 5, and then multiply those 3 together from each, and you get 180. So another neat method for factoring there, using the prime factorization method. All right, next we have example 4. Oh yeah, sorry, there's a check your understanding question. The answer is 252. All right, you can work that out, do either method. It's up to yourself. So example 4, it says solving problems that involve greatest common factor and least common multiple. So it says, what is the side length of the smallest square that could be tiled with rectangles that measure 16 centimeters by 40 centimeters? Assume the rectangles cannot be cut. So in the square, we're going to arrange the rectangles that have the same orientation to make the floor. So I'm going to get a picture, an idea of that and what it's going to look like. So that's what a tile would look like, 16 by 40. This is a square. So we want to know how can we make the sides the same. So what you're going to do is you're going to look for the least common multiple. And the least common multiple will give you the dimensions of the square, the smallest square that you can make with these tiles. Okay, so you can find the LCM for both. Very simple. LCM. So 16. It's going to be 16, 32, 48, 64, 80. Okay. And I'm going to stop there for a minute because 40 is going to equal, obviously, 40, then 80. So we found our LCM. It's going to be 80, so this side has to be 80 and that side has to be 80. So when you draw your diagram, it's going to look like this. So we have 5 multiples, 16, 32, 48, 64, then 80. So that's going to give us 5 tiles across this. We have 2 multiplies by 40. So 2 times 40 would give us 80. We'd have 80 by 80. So we'd need 10 tiles here. right? And the side length is 80 centimeters. So the answer to the question is the side length of the smallest square. The side length of the smallest square is 80 centimeters, as you can see from the diagram. So diagram helped me there. If you don't need it, that's fine. But you can clearly see that it works quite well. Okay. The next question says, what is the side length of the largest square that could be used to tile a rectangle that measures 16 centimeters by 4 centimeters? Assume the squares cannot be cut. Sketch the rectangle in the squares. So in this particular case, we're looking for the side length of the largest square that could be used to tile the small. So we're kind of looking inside this time, not outside, I guess, if that makes sense. So I'm going to get a diagram for an explanation. So in example 4b, we have our triangle here, our tile, 1640. We want to know how we can get squares within that that are the same. So now we're looking for, you probably guessed it, this time we're looking for GCF, right? So in the previous example, we're looking for LCM. In this example, we're looking for GCF. So the GCF of 16, so we write the common factors of 16. So 16 we know are 1, 2 times 8, 4 times 4, 8 and 16, right? So those are the 5 factors of 16. 4 is twice, because 4 times 4, so you only list it once. And now I'm going to do 40 this time. So 40 we know 1, 2 works, 3 doesn't, 4 works, 5 works, 8 goes with 5, 10 goes with 4, 20 goes with 2, and 40. So the GCF is the greatest common factor, which is 8. So that means these little tiles on the inside can be 8 by 8. So I will show that in the diagram as well. So since each can be 8, greatest common factor means each tile can be 8 by 8. So if we have 2 of them going this way, 8 plus 8 is 16. If we have 5 of them going this way, 5 times 8 is 40. So you can look at it 2 different ways from 2 different perspectives. One is you're finding the side length of the smallest square. This is the square here, so we're looking for the big square. They would have those tiles of 16 by 40. And the B part, we're looking for the side length of the largest square that could be used to tile a rectangle. So we're trying to tile this. Before we were trying to tile a square with tiles that were 40 by 16. This time we're trying to figure out how to tile have square tiles within this rectangular dimension. So you got to read the questions. Be careful there. A couple check your understandings to go with that. The answer to the first one is 70 inches. And the answer to B part is 4 inches. Done similar. Okay. And I guess I can answer that question over here. Side length of the largest square. Largest square is 8 centimeters. Okay. That's it for me, and that's it for chapter 3.1. There's some homework questions if you notice at the bottom there. There they are, back. Page 140, number 3 through 5, and then 8 through 17. And when you're doing 8 through 17, if there's multiple ones, you can just do the odd letters ones. But I recommend trying them all. It's completely up to yourself. So thanks again for watching. In the next video, we will pick up on the next section, which is 3.2, perfect squares, perfect cubes, and their roots. Thank you very much, and we'll talk again soon.